Welcome to our quantum deep dive. Today we're stepping into the fascinating, sometimes really mind-bending world of quantum information and quantum computing. And we're doing that by looking closely at a key figure, the theoretical computer scientist Scott Aaronson. Our guide for this is an essay by Jörg O. Shtetl-Optimized.
Yeah, it's quite a field, built on ideas from quantum mechanics, things like superposition, entanglement, concepts from the early 20th century that seem pretty counterintuitive at first, but these aren't just physics concepts anymore. They're really the core of how these potential quantum computers might work. Understanding them is, well, it's key.
Absolutely. And Schneppat's essay, I think, does a good job framing Aaronson's specific role in all this. Aaronson's been pivotal, hasn't he? Especially in figuring out, rigorously what quantum computers might actually be capable of, and just as crucial, what their limits might be.
Yeah, exactly. So this deep dive, it's based on Schneppat's analysis of Aaronson's contributions, their implications practical and theoretical, and the future challenges. Shnepat breaks the essay down into about 5 main sections, and we'll kind of follow that structure.
Okay, sounds good. Let's jump in. Shnepat starts with a quick recap of the quantum basics. Not too deep, just the essentials for computation.
Right. The fundamental difference is moving from classical bits, always a definite 0 or 1, to qubits.
Qubits. And the key thing there is superposition, right? That ability to be somehow a combination of 0 and 1 at the same time.
Precisely. Shnepat reminds us it's not just maybe 0 or 1, it's really existing in both states until you measure it. That's the basis for what they call quantum parallelism, the idea that a quantum computer can sort of explore many paths simultaneously. Shnepat mentions the math too, describing this state as a blend. Alpha times the state 0 plus beta times the state 1.
And then there's entanglement, which is still just wild to think about.
It is. That deep connection between qubits. Measure one, and you instantly know something about the other, no matter how far apart. It's like they share a single destiny. Shnepat really emphasizes this isn't just theory. It's critical for quantum power and for secure communication protocols.
But there's a big catch, as Shnepat points out, coherence.
Oh, yeah. Keeping that qubit in its delicate superposition state. Incredibly hard. Any little thing, external noise, temperature shifts, tray fields, can cause decoherence. The quantum state collapses. You lose the advantage. It's a massive engineering challenge.
Shnepat does a nice job tracing this back, from the quantum pioneers, Planck, Einstein, Bohr, Schrödinger, to the people who first thought about applying it to computation, like Feynman and Deutsch.
Right, and he highlights how those early algorithms, like Shor's algorithm for factoring,
which is the one that threatens current encryption.
Exactly. And Grover's algorithm for searching databases, they really showed the potential. They demonstrated that quantum machines could offer, exponential speedups for certain kinds of problems.
Yeah, those algorithms proved it wasn't just theoretical physics anymore. It had computational teeth, so to speak, which, Shnepat argues, leads us right into Scott Aaronson's main contributions, focusing on quantum complexity theory.
Right. Shnepat frames Aaronson's work as asking this fundamental question. What exactly can quantum computers solve efficiently? And how does that power compare to classical computers? It's about mapping out the landscape of computational problems from a quantum perspective.
Kind of like how we have classical complexity classes, P for problems solvable quickly, NP for ones where solutions are easy to check, and that big famous P versus NP question, are they the same class?
Exactly. And Shnepat shows how Aaronson really dug into defining and understanding the quantum equivalent class. BQP. That stands for bounded error quantum polynomial time. Basically, the set of problems a quantum computer can solve efficiently with a high probability of getting the right answer.
And Shnepat highlights a major result from Aaronson here.
Yes, proving that BQP is distinct from P, and likely distinct from NP too. Shnepat stresses this wasn't just like an academic point. It mathematically confirmed that quantum computers aren't just faster classical machines. They operate differently. They can tackle problems, like factoring large numbers for Shor's algorithm, that seem fundamentally intractable for classical computers.
Though the exact relationship, Shnepat notes, between PNP and BQP is still an open research question.
Definitely. Still lots to figure out there.
Okay, so this leads Shnepat into discussing something really interesting. Quantum hardness and the push for quantum supremacy, or maybe quantum advantage is the preferred term now.
Yeah, quantum advantage is often used now. Quantum hardness looks at problems tough even for quantum computers, and quantum advantage is that specific milestone. Getting a quantum computer to perform any task, even a contrived one, that's practically impossible for the best classical supercomputers today.
Right, performing a calculation that would take a classical machine thousands of years, maybe.
Exactly. And Shnepat points out how Aaronson provided crucial theoretical groundwork for demonstrating this advantage was possible. He showed you could design specific computational tasks where quantum computers provably have that edge, confirming the theory wasn't just hypothetical.
And we saw a practical step towards that in 2019, right, with the Google experiment. They claimed their quantum processor did a specific task in minutes that they estimated would take a top supercomputer, 10,000 years. Shnepat discusses this as a landmark.
It was a huge milestone, yes. A demonstration on a specific, carefully chosen problem. But Shnepat is also careful to include Aaronson's own perspective here, which is always quite nuanced, quite cautious.
Right, he's enthusiastic but also realistic about the hurdles.
Very much so. Aaronson constantly emphasizes the massive practical challenges that remain. Decoherence is still a huge problem, and building fault-tolerant machines requires incredibly effective quantum error correction. These aren't minor engineering tweaks. They're fundamental scientific and engineering barriers.
Shnepat also briefly mentions Aaronson exploring beyond BQP, the post-BQP realm.
Yeah, asking about the ultimate limits of computation itself. What if quantum mechanics allows even stranger forms of computation? It gets into really deep philosophical territory about computation and reality.
So we have this theoretical landscape mapped out, largely thanks to Aaronson. Where does Shnepat say this leads in terms of, real-world impact, applications? Let's start with the big one everyone talks about, quantum cryptography.
Yeah, Shnepat dedicates quite a bit of space to this, and for good reason. It's urgent. The threat is clear. A sufficiently powerful quantum computer running Shor's algorithm could break most public key encryption we rely on today. RSA, for instance.
Which protects everything from online banking to government communication.
Everything, because it relies on the difficulty of factoring large numbers for classical computers. Quantum computers make that easy.
And Aaronson, according to Shnepat, has been a very vocal advocate here, right? Sounding the alarm.
Absolutely. He's stressed the urgent need to develop and deploy post-quantum cryptography, or PQC. These are new classical algorithms based on different mathematical problems, things like lattices, codes, hashes, that we believe are hard for both classical and quantum computers to break.
But developing and standardizing those takes time and effort.
Huge effort. There are challenges in implementation, performance, getting global agreement on standards. It's a major ongoing transition.
And Shnepat also mentions that quantum mechanics isn't just the threat here, it also offers potential solutions.
Right, like quantum key distribution, QKD. This uses quantum principles like entanglement to securely share encryption keys. The neat part is that the laws of quantum physics guarantee that any attempt to eavesdrop inevitably disturbs the system, alerting the legitimate users.
So it offers a fundamentally different kind of security. Aaronson sees this as a key practical application.
Yes. Shnepat suggests Aaronson views QKD as a place where quantum tech can offer immediate security benefits, complementing the move to PQC.
Okay, beyond security, what other applications does Shnepat highlight? Quantum simulation seems like a big one.
Potentially the most impactful near-term use, according to Shnepat, and reflecting Aaronson's views. It makes sense, really. Simulating complex quantum systems, how molecules behave in chemistry, designing new materials that's exponentially hard for classical computers.
Because you're trying to simulate quantum using classical bits.
Exactly. But quantum computers are quantum systems themselves. So they're naturally suited to simulating other quantum systems. It's like using the right tool for the job.
And the potential impact there is enormous.
Huge. Accelerating drug discovery by simulating molecular interactions, designing materials with specific properties from the ground up, improving catalysts for industry. Shnepat really emphasizes Aaronson's perspective that simulation is probably where we'll see the first major, widespread, real-world quantum advantage.
Shnepat also brings up Grover's algorithm again for optimization and search. Things like logistics, maybe data analysis.
Yes, it offers a quadratic speedup for unstructured search, which can be valuable in optimization problems across various fields, although the speedup isn't as dramatic as Shor's.
Now, Shnepat also connects Aaronson's theoretical work back to the practical nitty-gritty building the hardware and software.
Definitely, because all this potential relies on actually building working quantum computers, and overcoming decoherence and errors is paramount. Aaronson's theoretical work, particularly on complexity and noise, directly informs the critical research into quantum error correction QEC. We need QEC to build stable, fault-tolerant machines.
It's not just about having more qubits, but better error-corrected qubits.
Exactly. And Shtetl also touches on the current trend of hybrid systems. Given the limits of current quantum hardware, many approaches involve using quantum processors as specialized accelerators alongside classical computers. Aaronson's theoretical understanding of BQP and its relation to classical classes helps provide a foundation for designing and analyzing these hybrid models.
And Shtetl points out, Aaronson's influence isn't just academic, it extends to the major tech companies and startups racing to build these machines. His theoretical insights guide practical development.
For sure. His work helps define the targets and understand the challenges they're facing.
Okay, so that brings us to the broader societal and ethical implications that Shtetl discusses. It's not just about the tech itself.
Absolutely critical point Shtetl raises. Data security is probably the most immediate concern. Imagine critical infrastructure, financial systems, private data suddenly becoming vulnerable.
Yeah, the implications are staggering.
And then there's the impact on jobs. Fields like cybersecurity, material science, drug discovery could be transformed. That means potential disruption, the need for retraining, new skills. Shtetl also flags the risk of concentrating power, who controls this technology, who gets access, what regulations are needed to prevent misuse, for example, in code breaking by hostile actors.
Shtetl notes that Aaronson is very engaged with these issues, advocating for responsible development.
Yes, a strong advocate for transparency and thinking through the consequences. Shtetl highlights Aaronson's urgent call. Governments and companies need to get serious about developing and deploying quantum-resistant crypto now, proactively, not waiting until the threat is imminent.
He sees it as a race we need to win.
Definitely. And beyond crypto, Shtetl emphasizes Aaronson's push for open science and accessible education in quantum computing. The idea is to ensure broader societal understanding and prevent this powerful technology from being locked away, understood only by a few. It fosters trust and allows for more informed public discussion.
Which connects back to Aaronson's philosophical side, right?
Exactly. Shtetl mentions Aaronson's engagement with those deeper questions. What does quantum computing tell us about the nature of computation, information, even physical reality itself? He encourages that broader public discourse.
So looking forward, where does Shtetl see this all heading? Building on Aaronson's work and insights, what's the future outlook?
Well, the key challenges remain front and center in Shtetl analysis: quantum error correction and scalability. We need to get much better at controlling noise and building larger, more robust systems with many high-quality interconnected qubits. That's still a huge mountain to climb.
But there are promising directions, too.
Oh, absolutely. Shtetl points to continued progress in developing more sophisticated quantum algorithms beyond just Shors and Grovers. And the ongoing work on those hybrid classical quantum systems looks very promising for extracting value from near-term noisy quantum devices.
And Shtetl presents Aaronson's vision for the future as, well, grounded, realistic.
Very much so. Fault-tolerant, universal quantum computers capable of solving any BQP problem are likely still a long-term goal. Aaronson often talks about quantum-assisted classical computing. He envisions quantum devices acting as powerful, specialized coprocessors.
So not replacing your laptop, but maybe a specialized chip in a supercomputing center or a cloud service.
Exactly that kind of model. They'd tackle specific sub-problems where they have a distinct advantage working alongside classical machines.
So how might we see this integration in industry and maybe eventually daily life, according to Shtetl?
In industry, Shtetl suggests we'll see them used as specialized tools for optimization. In complex logistics, supply chains, maybe financial modeling for risk assessment. Also, obviously, for secure communications and data security, perhaps through PQC deployment influenced by the quantum threat, or potentially QKD networks.
And for daily life, probably more indirect impacts.
Yes, likely through breakthroughs enabled by quantum simulation in industry or research, revolutionizing medicine via faster drug development or personalized treatments based on molecular simulations, or creating novel materials with amazing properties that eventually find their way into consumer goods or infrastructure.
So the key takeaway Shtetl emphasizes is they won't replace all classical computers. They'll be incredibly powerful tools for specific, complex problems where classical methods hit a wall.
Precisely. They augment classical computing power, opening up new frontiers rather than replacing it wholesale.
Okay, so to kind of wrap up this deep dive, Schneppat's essay really paints Scott Aaronson as a central figure in defining this whole field, rigorously analyzing BQP, providing that theoretical basis for quantum advantage experiments, really hammering home the urgency of quantum-resistant crypto, and also consistently highlighting those huge practical challenges like error correction.
Absolutely. Schneppat underscores that Aaronson's work provides an essential theoretical framework. It helps us understand not just the incredible potential, but also the fundamental limits of quantum computation. That framework guides the technical development, yes, but it also forces us to grapple with the profound ethical and societal questions. His work really helps define quantum computing as a truly new paradigm, not just, a faster version of what we already have.
And beyond the pure science, Schneppat portrays Aaronson as an important leader and communicator, bridging that gap between incredibly complex theory and broader public understanding through his writing and outreach.
He plays a vital role there, making these ideas accessible.
So here's a final provocative thought for you to consider, stemming directly from Schneppat's discussion and the implications of Aaronson's work. If quantum mechanics fundamentally changes the very definition of what is computable, as Aaronson's work explores, does that also inherently shift our fundamental understanding of the physical reality in which that computation takes place? Something to mull over. Thank you for joining us on this deep dive into the world of Scott Aaronson and the quantum frontier, guided by the insights from Jorgo Schneppat's essay. Goodbye.